Hello math enthusiasts, welcome to another video. In this section I'm gonna to prove that the Lagrange equation, and it's so useful in classical mechanics when you consider, for example, something like this. I don't know, something like this with slope, and in the here you don't know what is this normal surface, and you have some constraint in your slope, and you can write by the F equal ma, and it's so hard. Therefore, in this section I'm gonna to discuss how this formula produced, and you can use in a state of F equal to ma. But what is the formula? The formula is exactly d dt dl dq e dot minus dl dq equal to 0. Therefore, if you gonna to use in a state of F equal ma, in some condition you can use this formula, and it's so applicated than this one, because I told you if you have in polar coordinate you never can use this and it's so hard, or if you have a constraint immediately you can use the constraint in your formula and you must use this. But what is the L exactly? L is T minus U, kinetic energy minus potential energy. Therefore, in this formula, in this top formula, we're gonna to prove that exactly you don't see any force, and we just work with kinetic energy and potential energy, guys. But before we go to that, let's explain some things. What is the virtual work? At the first, you consider you are one particular in here, and you gonna to describe this not only in coordinate, Cartesian coordinate, in polar coordinate. Your axis is q1, q2, q3, or qm in the time t. For example, this particle in every time, and it has some coordinate in polar, is something like polar coordinate. For example, in this shape you see a double pendulum. Yes, this L, and is something like this M. You see at the first your coordinate is with respect to x and y, but you change it with W theta 1 and theta 2, and therefore you can write instead of x is L cosine theta 1, because it's exactly this one, and instead of y is L sine theta 1, but instead of this part add with this part, of course. You see, instead of you write the x2 and L2, you consider, for example, that is x2 and that is L2. If you're gonna to write this, is something like this. It's not in our proof, guys. I just you gonna to understand this, what's the meaning of this. For example, when you have a particle, your theta 1 and theta 2 is exactly in double pendulum, is your new calculation, and is your q1 and q2. But I think I write all the detail in here, and I'm gonna to explain in the here better. But I told you, yes, when you have any particle in the here, you can write it by q1, q2, and qk, and with respect to time. But we have something is so important, you must know. You have a displacement, two type of displacement, the virtual displacement and actual displacement. What is the difference between them? But I told in the note that consider that if a placement is true and is dr, the displacement is not only for with respect to q but also with respect to t. Therefore, our calculation is dr divided dqi times dq and plus, and the t place is dr divided dt times dt. Exactly, that is dr, the placement of with respect to all of things. But what is the virtual displacement, guys? You consider, you take a snapshot from all the motion. For example, your motion is something like this, and you just take a snapshot in here, and you just gonna to see the placement in this time without changing the time, and you just gonna to see this displacement with respect to change of the r, or with respect to qi, it's better to say. And therefore this part is cancelled, guys, and that is just our virtual displacement is something like this. But if you're gonna to consider, we have two type of the force, and in every physical motions we have two type of the force, active force and constraint force. What is the strategy in here? I gonna to because in the virtual works, the virtual works, when we have no friction like this, the virtual work is 0. Therefore, the active, the constraint force also is 0, because the constraint force is exactly force times the virtual work is exactly force times sigma ri. Yes, when all of these is 0, therefore the constraint force is 0. Therefore all this part cancelled, and we just work with active force in the here. Okay, therefore I told you this part is 0, and therefore I cancel this part. Excuse me, I cancelled this part, and we just work with this part. But one more thing is so important, and the Lombard principle. What is that exactly? I think I can pronounce it good or not, the Lombard or something. What is the meaning of this? You know, in every escalating, you have an inertial force exactly opposite side of the time, and the idea is this: when you take a snapshot, in every time when you go and down and something, you do a snapshot, and that is exactly in the same position, and the force is exactly that force, but is in the in front direction. For example, I told you, you have something like this. In this time you have a force, but if when you take a shot, you consider that is an equilibrium point, but the force, the initial force is exactly the same, but in the opposite side. Therefore is Fi minus MII is 0, because we are in the equilibrium point. Is also is a hypothesis that's imaginary. I think I can say better that is imaginary. And what this time in this calculating is so important, guys. I gonna to tell you, I tell all the things in here, but we know this because we are in the equilibrium point, that is 0, but we separate f sigma ri to another part, but mi, this part exactly, times with sigma ri to another part, and we call this exactly ql. We write this name ql, but we're gonna to calculate exactly this part, guys. We work with this part. And this part exactly is so important for us, because right now we're gonna to work exactly this parenthesis times with this part. Okay, let's to explain and calculate it. At the first, I explain all these things, but I told you this part we call the QL. But what is the QL? Also, you know, if you're gonna to take a derivative from potential energy with respect to new polar coordinate, the potential of U exactly is F. yes, but therefore the ui, run the partial derivative of ui to partial derivative of q with a minus exactly is ql we calculate in the previous one. Yes, okay, but we are right now in the important part of our calculation. What is that exactly? Guys, I told you we just gonna to calculate this part, and after calculation this part we can take something like this. We're gonna to find the T kinetic energy near and inside this formula. How we can write this? At the first we know we are in this section mi ai partial derivative of r with respect to q, but if we multiply this they can cancel and exactly our previous one. Yes, okay, but we can write this is something like this. Why we use this rule in the derivative? I don't know, v times is exactly, v prime m plus m prime v. Yes, therefore if I put this part in the right side, exactly is v prime m minus this this value with the derivative. Exactly, guys, that is something like this. If you're gonna to write this is mi vi with this, and you write and use this identity, you can receive to this value. I don't gonna to explain because it's so much, but something in here is so important, guys. In a state of this calculation, what I write it, I at the first divide it to the t. If you divide it to the r to the t is a v, but q, if you divide it to the t, I write it by q dot. Okay, therefore in a state of this I can write dv divided to dq dot, but if you're gonna to take derivative from partial derivative of r divided to the q, exactly is not hard because derivative of r is v. Yes, when you go to when you go and in every physical movement, when you take a derivative is velocity, is not so hard. Therefore in a state of this we substitute in here. In a state of this I write this part in the here, guys, and in the state of this I write dv divided to dqi. But I take the integration. If you consider this, if you're gonna to take derivative from this part, exactly is this. Yes, okay, I take an integration from this part is 1 over 2 mi, because mi is a constant and is a mass, and come out the calculation. Therefore this value derivative is exactly this, and instead of also this I can write this part but with respect to qi, but another one with respect to q dq dot. Yes, because we have a dot here. Okay, but in here we have dt. In a state of this we achieve to what things? Yes, that is a kinetic energy. Also this part is kinetic energy, but our calculation receive to this dt d to dt divide times partial derivative of t with respect to qi minus partial derivative of t with respect to q. Yes, but minus q l. Why? Because we write that is inertia force, and that is exactly f a dot times sigma ri. What exactly this part, guys? Let me show you in the here, because write it. Okay. In the here I named this part. Yes, in here, I write this part QL, but we separate each other. But right now we add all of them. F equal to F and MR, we separate each other and multiply with displacement, virtual displacement, and right now add together, answer is 0. Yes? Okay, because we are in the equilibrium point. Okay, but if we add right now this part, but my computer has a little lag. Okay, but if I add this part, exactly I put in the right side, but it's not important right now. But instead of these, we can write what things? du dqi with a minus. Yes, because I told you the derivative of potential energy is exactly F, and instead of QL we can write this. Okay, I write it in the here. Yes, therefore we can add to the both sides, because the potential energy is just respect to QI, guys. We in the potential energy is everything is with respect to QI, not QI dot. We hadn't any derivative in potential energy formula. Therefore this value is 0, and immediately I can add this part with respect to QI in here without the changing the formula, and also I can add this part to the second part, and we write this T minus U, we say the L, what's the meaning of is Lagrange equation, and our total formula can change to this dt dl divided to dq dot minus dl minus dq I equal to 0. Exactly, that is our formulation for Lagrange equation when we have no friction. If we have a friction, our formula change to this part is not 0, guys. Is something is when we had it's so harder to calculate that this. But I told you this just a typical explain, you can understand how the Lagrange equation appear. But if you're gonna to understand it better, also 2 days ago I solved this question also, but if you're gonna to understand better, you must solve a lot of questions to use this formula, because for example in double pendulum also you can find, if you're gonna to calculate this formula with F equal ma is so hard, but if you find the x and y with respect to theta 1 and theta 2, and after that write this formula d to d theta, for example dl d theta 1 dot minus dl dq d theta 1 equal to 0. Yes, and also for theta 2 also you write this equation and after that solve the question. It's not so easy, but it's practical when the question is so hard and you have a constraint, because if you see the double pendulum it's so complicated and you can calculate by the simple Newton formula. I wish you all the best. Have a nice day. Take care. Bye bye.